Hey guys, so welcome back to your next class. In the previous class, we looked at something called the Mendeleev's periodic law, Mendeleev's periodic table and the law that was stated by him as the Mendeleev's periodic law, or simply just the periodic law, right? So today we're going to look at how that form of table had advanced and became into today's model that we see, which we call as a modern periodic table. Okay, so let's recap what was the periodic law that we had studied last time. It said that the chemical and physical properties of elements are a periodic function of their atomic weight. Right? It repeats based on its atomic weight. As the weight progresses, the properties will repeat after a certain interval of time, is what they were saying. Now, there was a slight modification to this by a scientist named H.J. Moseley. Okay, so what Moseley did was he used an experiment in which he was taking different elements, and he was throwing high energy electrons at these atoms. Okay, throwing these electrons at these atoms of these elements. What he noticed was whenever you do that, each element will give out something called X-rays. X-rays are one type of electromagnetic wave that we had studied in the electromagnetic spectrum part. Now, each element has a unique X-ray spectrum, right? So he said that uh, this unique X-ray spectrum that is coming because of the nucleus, and the nucleus is the place that holds the protons. So what his conclusion is that it is not simply the atomic weight, but more the number of protons that will define this periodicity. Okay, so the number of protons is nothing but the atomic number. Okay, the atomic number of an atom is simply but the number of protons in the nucleus for that atom. Okay. So what he said, he changed the periodic law in a slightly different way. He said the physical and chemical properties of elements, I'm just writing it in short here, are a periodic property of their atomic number. Okay. So for example, if you talk about hydrogen, we say atomic number 1. It means hydrogen has only one proton inside of its nucleus. Similarly, atomic number 2 is helium, means helium has two protons inside its nucleus. Okay, now if you parallel this atomic number with instead of protons, in a neutral atom, we have seen in I think the the Bohr's model part, we have seen that we draw electrons outside, right, in a neutral atom. So usually the protons and electrons are equal in a neutral atom. So if there are 10 protons inside the atom, inside the nucleus, there will be 10 electrons outside the nucleus. In the normal state, for example, hydrogen, when we draw one electron outside. It also has one proton inside. Okay. If you talk about helium, it has two protons inside and also two electrons outside. So in the neutral state, atomic number can also be the number of electrons of the atom in its neutral state. So the difference over here, why we are talking about protons and electrons, is in an atom, protons are fixed. They do not change. But the electrons can change based on how the atom reacts with other atoms, right? If you've seen, we talk about energy levels also, like atoms sometimes jump, so electrons jump to a higher levels and come back to a lower level, absorb energy. So because of that also, we can say ki, yes, there are definitely changes in properties. So a slight more advancement of this we can also say is that physical and chemical properties of elements are a periodic function, not property, periodic function of their electronic configuration. Okay. We can talk about it in both ways, not just one. But if you talk about the statement, it is with atomic number. All right. So based on this, they slightly modified the periodic table and made a new modern periodic table. So we're going to look at what are the major two aspects of this periodic table. I'm just going to show it to you over here. So this is a simple diagram of the periodic table. So this is a representative. We'll show you. Each block signifies one element. H, the big alphabet, is the symbol. The small number on top is the atomic number of that element. Below it is the name of the element, and much below it is which group it falls under, which is not really visible, but that's fine. Okay, if you zoom in, it will be, but that's not really necessary right now. Okay, so if you can see, it's a bit of an odd shape, right? If I have to draw it, I'll have to draw it something like this. I'll be like, oh, it looks something like this, and then there is something like this at the bottom, right? Which looks very peculiar, but there is a reason why they're drawn it like this. Okay, so firstly, let's talk about what are the horizontal and the vertical. Okay, so again, we use the same terminology that Mendeleev had used. We'll talk about groups and periods. Okay, now groups are vertical, exactly like how Mendeleev had said. So there will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Right? If you count it, you will find there are 18 vertical columns. Okay. So vertical, and there are 18 groups in total. All right. There's a different numbering for 1 to 18. All right. Now, what is special about these groups is, again, just like Mendeleev had said, you just get like similar properties when you looking within the elements of the group. All right. Now, what is periods then? It is nothing but horizontal, just like Mendeleev had said. And there are how many of them? 1, 2, 3, 4, 5, 6, 7. Okay, these are not part of the table over here. They will be within. Okay, so there are 7 horizontal rows. Okay. So those will be the periods. Okay. Now, this is the basic structure of our what do you say, periodic table. Now, one very important thing that you need to notice here is there's a different coloring given to each block. There's like a weird coloring, right? It's not all the same color. Okay, within the periodic table we have a certain differentiation and a certain reason why they are arranged like this. Why does this row have only 2? Why does this have 8? Why 8 here again? Why this gap? And again, why does this have more than 8? Why does it have 8? This will be 18 over here. Okay, and this overall this whole thing has a reasoning. Okay, let's try to follow this logic. Okay, all of this is based on nothing but the electronic configuration, which is again one word that we used over here. So if I use the electronic configuration of an element, the last electron of that atom is going to decide where it falls. Okay, so if I talk about hydrogen, we remember its atomic number is 1, so we write it as 1s1. Okay, you see that the last one falls in S subshell, correct? So hydrogen as an element is going to fall in either of these two rows. So these two columns over here, 1 and 2, right? hydrogen, lithium, all of these, beryllium, magnesium, calcium, all of these. This is called as the S block. So any element whose last electron is in S subshell is going to fall under any of these two columns. Again, dependent on their atomic numbers. Okay, so atomic number 1 is here, 2 is coming right beside it, but at the end. Then 3, 4, 5, 6, 7, 8, 9, 10. Horizontally, it is the increasing order. Okay. Now, if we talk about the electronic configuration again, let's look at something like oxygen. Okay. So if I talk about oxygen is 8. So 1s2, 2s2, 1, 2, 3, 4, 5, 6, 7, 8. Okay. 1, 2, 3, 4, 5, 6, 7, 8. This is the electronic configuration of oxygen. The last electron is falling in P, right? So that is why this oxygen is in the P block. This entire block over here from group 5 all the way to group, so not group 5, but yes, this group from boron all the way till this helium. These last 6 are called as the P block. Similarly, if we follow the one in the middle over here in the blue color, from scandium Sc all the way zinc, all of these boxes are called D block, following the same logic key. Last electron, if it falls in D, then it will be in D block. Now same way, this last one at the bottom is called as the F block. Okay, they kind of join over here, and they will kind of continue like that all the way. Okay. So there is one connection between how many elements are there horizontally in each block and the subshell itself. What I'm going to do, I'm going to leave that as a trick kind of thing for you to figure out. Okay, if you are able to figure out why is S block only this much, why is P block this much, why is D this big, and why is F the biggest. If you can figure that out, please drop it in the comment. I'm going to tell you tomorrow anyway. So this is where I'll stop the class for today, and I'll see you in the next class. Okay, thank you.